Welcome to True Projects. In this video, we are going to explain about the project entitled as Predicting Diabetic Retinopathy and Nephropathy Complications Using Machine Learning Techniques. So before getting into the video, let me give you the brief description about the project. This study focuses on using machine learning techniques to predict diabetic retinopathy and nephropathy by analyzing clinical and patients' data. Early and accurate prediction aims to support timely intervention, improve disease management, and reduce the risk of severe diabetic related complications. Coming to the abstract explains that diabetes can cause serious complications like eye and kidney damage if not identified earlier. It highlights the limitations of traditional diagnostic methods, which are often slow, expensive, and dependent on expert evaluation. To address this, the study proposes using machine learning techniques to analyze patient clinical data and detect patterns that indicates the risk of diabetic retinopathy and nephropathy at an early stage. This approach aims to improve prediction accuracy, assist doctor in making better decisions, enable timely treatment, and ultimately reduce the impact of diabetes related complications. Coming to the existing system for diagnosing diabetic retinopathy and nephropathy mainly relies on traditional clinical procedures and expert evaluation. Diabetic retinopathy is identified through manual analysis of retinal fundus images by trained ophthalmologists, while diabetic nephropathy is diagnosed using laboratory investigations such as urine album test and serum citrine measurements. Although these methods are clinically reliable, they require specialized equipment, skilled professionals, and repeated testing, which makes the process time consuming and costly. Access to such diagnostic facilities is often limited in rural or under-resourced areas. Moreover, the current system is largely reactive as it detects complications only after noticeable disease progressions, leading to delayed intervention, reduced treatment efficiency, and increased long-term healthcare burden. Coming to the proposed system or base paper work, the proposed system uses machine learning techniques to predict the early risk of diabetic retinopathy and nephropathy by analyzing patients' clinical data. It applies supervised learning algorithms such as support vector machines, random forest, logistic regressions, and neural networks to detect complex patterns related to disease progression that may not be easily identified through traditional methods. To enhance prediction accuracy, the system incorporates data pre-processing and feature selection techniques that removes noise and select the most relevant clinical parameters. This automated and data-driven approach enables faster and more accurate risk assessment, supports clinicals in making informed decisions, and allows for early intervention and personalized treatment plans. As a result, the proposed system helps reduce the severity, progression, and overall impact of diabetic related complications on patients. Coming to the data set, we have used two different data sets. One is text-based data set and other one is feature-based data set. First, the text-based data set is named as Cravled Links dataset. The Cravled Links dataset is a text-based dataset created by collecting web links through an automated web crawling process. Its primary focus is on the textual representation of URLs and the structural relationships between web pages. Each data entry generally represents a hyperlink connection showing how one web page points to another. This dataset helps in understanding the connectivity of the web by capturing information such as source pages, target links, and sometimes additional metadata related to the links. Because the dataset is dominated by text data, it is well suitable for text mining, natural language processing, and web structure analysis. Researchers can use it to analyze hyperlink patterns, detect malicious or suspicious URLs, study website navigation structures, or construct graph-based models that represents the relationships and influence among different web resources. Next, feature-based dataset. It is named as Network Packet Direction and Timing Dataset. The network packet direction and timing dataset is a feature-based dataset derived from network traffic observations, where each record represents measurable characteristics of data packets transmitted over a network. Instead of raw textual information, the dataset contains structured numerical and categorical features such as packet direction and timing related attributes like packet arrival times or time intervals between packets. These features describe the behavior of network communication flows and allow patterns in traffic to be captured quantitatively. This dataset is particularly useful in machine learning and cybersecurity domains as it enables the detection of abnormal traffic behavior, identification of network attacks, and classification of different types of network activities. By analyzing direction and timing features, models can learn how normal network communication behaves over time and identify deviations that may indicate performance issues or security threats. Coming to the novelty or extension or enhancement or improvement. The extension of this project enhances the original system by introducing an advanced machine learning ensemble of ensembles model to further improve prediction accuracy and robustness. In addition to numerical clinical data, image processing techniques were incorporated using a diabetic retinopathy dataset, where deep learning models were developed to classify retinal images into DR and no DR categories, achieving very high accuracy between 98% and 99.9%. The system also provides recommendations outputs based on numerical data predictions to support better disease management. Furthermore, explainable AI techniques were implemented to improve transparency and trust in the models. Lime and SHAP were used to explain feature importance for numerical data, while GradCam was applied to image classification models to visualize highlight important regions in retinal images through heat maps displayed in the user interface. Finally, a Flask-based web interface was developed, allowing users to input data and receive predictions and explanations interactively, making the system more accessible and user-friendly for clinical decision support. Coming to the flow of the work, first, we need to import the packages. This module involves importing all the required Python libraries like data handling, visualization, machine learning, deep learning model, evaluation, and deployment. These libraries support tasks such as pre-processing, training models, performance evaluation, explainability, and front-end integration. Next, exploring the dataset. In this module, the diabetic retinopathy nephropathy dataset is loaded and explored to understand its structure, feature type, target variables, and overall distribution. This step helps identify missing values, class imbalance, and data patterns before further processing. Next, data pre-processing. This focuses on cleaning the dataset. Missing values are handled using suitable implementation. This module focuses on cleaning the dataset. Missing values are handled using suitable imputational techniques and outliers are detected and treated to reduce noise. Proper pre-processing ensures higher model accuracy and reliability. Next, data visualization. Visual analysis is performed in this module to gain insights into the dataset. The distribution of classification outcomes helps understand class imbalance while the correlation matrix highlights relationship between features, aiding in feature selection and model understanding. Next, feature scaling. Feature scaling is applied using the minimax scaler to normalize all numerical features within a specific range. This ensures that features contribute equally during model training and improves convergence for certain algorithms. Next, data splitting. The dataset is divided into training and testing subsets. This module ensures that model learning and evaluation are performed on separate data to avoid overfitting and provide unbiased performance results. Next, resampling the data. To handle class imbalance, this module applies smart oversampling to increase minority classes samples and random undersampling to reduce majority class samples. Balanced data helps improve model generalization and prediction fairness. Next, grid search cross validation. This module performs hyperparameter tuning using grid search with cross validation. It systematically evaluates multiple parameters combinations to identify the optimal settings that improve model performance. Next, classification model development. In this, multiple machine learning models are built and trained using original, oversampled, and undersampled data sets. Models including logistic regression, random forest, XGBoost, LightGBM, CatBoost, and MLP. Ensemble approaches such as voting and stacking classifiers are also implemented to enhance predictive performance. Next, ensemble of ensembles extension. This advanced module develops an ensemble of ensembles model using oversampled data. It combines multiple base classifiers through stacking and voting strategies, resulting in a more robust and accurate predictive system. Next, model evaluation. All trained models are evaluated using classification reports, confusion metrics, and performance metrics such as accuracy, precision, recall, F1 score, AUC, RMSE, and log loss. Numerical and visual comparisons are used to identify the best performing model. Next, model saving. The best trained model is saved for future predictions and deployment. This ensures consistency in results and allows seamless integration with the front-end application. Next, explainable AI visualization. Explainable AI techniques such as line and shape are applied to interpret model predictions. This model provides clear insights into feature importance, improving transparency and supporting trustworthy clinical decision making. Coming to the image classification, firstly, we need to import the packages. All the required Python libraries for data handling, visualization, machine learning and deep learning models evaluation and deployment. Firstly, we need to import the packages. This module involves importing all the required Python libraries for data pre-processing and deployment. These libraries support tasks such as pre-processing, training models, performance evaluation, explainability, and front-end integration. Next, exploring the data set. The APTOS 2019 Diabetic Retinopathy image dataset is loaded and analyzed to understand image classes, quality, and distribution before training deep learning models. Next, image data augmentation. This module applies image pre-processing and augmentation techniques such as resizing, rescaling, shear transformation, zooming, horizontal flipping, and reshaping. These techniques improve model generalization and reduces overfitting. And next, build a model. Deep learning architectures including ResNet 50, DenseNet 121, Exception, and NASNet Large are built. An ensemble model combining Exception and DenseNet 121 is also developed to enhance classification accuracy. Next, we have building and training the model. All the given image classification models are trained by using the algorithms. Next, comparing the models with accuracy, precision, recall, and F1 score. And finally, performance comparison graphs are generated to visualize and analyze the results. Coming to the front end, a user-friendly web interface is developed using the Flask framework. User registration and login functionality are implemented with SQLite database, support for secure access. This module handles user input of numerical feature values and retinal images. Inputs are pre-processed to match the format required by the trained models. The saved trained models are used to generate predictions based on user input. Final results, explainable visualizations, and drug recommendations for numerical data are displayed through the front end, completing the end-to-end system. The algorithms used in the project are: for classification, we use logistic regression, random forest, XGBoost, light GBM, cat boost, MLP, outing classifier, which consists of logistic regression, random forest, XGBoost, light GBM, cat boost, and MLP. And stacking classifier consists of XGBoost, random forest, cat boost, and light GBM. And for image classification, we have used ResNet 50, DenseNet 121, exception, NASNet large, and ensemble technique, which includes exception plus DenseNet 121. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to execute the Python script and perform a runtime check for any syntax errors. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. So this is the homepage of the project, should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have Home button and Get Started button. Now click on Get Started button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on Create an account so that all the given details are stored in signup.db and the login.html will be opened, where we need to access the application by username and password. The prediction page has been displayed. In this page, we have Home button, Prediction Modules button, Data Visualization button, Notebooks button, and Sign Out button. Firstly, click on Prediction Modules button As we are doing both prediction and classification, the prediction and classification are displayed. So let us check one by one. First, click on prediction button so that the prediction form will be open where you need to enter the patient information. Firstly, gender will be male, age is 53, diabetes duration is 8, smoking is yes, drinking is yes, height is 172, weight is 72.5, BMI will be 24.5064899. SBP value will be 156, DBP value will be 96, HbA1c value will be 10, FGB value will be 1.024, TG value will be 1.76, C-peptide value will be 0.94, TC value will be 4.4, HDLC value will be 0.9, LDLC value will be 2.85, insulin value will be yes, metformin value will be no, lipid lowering drugs is also no. Now click on predict retinopathy button so that the input is pre-processed and the output will be displayed as the given patient details are displayed as retinopathy is predicted 95.5% and nephropathy is detected as 93.6%. And we also have the other additional informations like immediate actions, what need to be taken, and specialistic consultation. We also have that retinopathy is detected, what is diabetic retinopathy is given, recommended actions are given, risk factors are given, and nephropathy detected, what is diabetic retinopathy, what is diabetic nephropathy, the recommended actions for that, and the drug recommendations are also given along with retinopathy treatment options, nephropathy treatment options, combined treatment considerations. And next we have new prediction. As we have seen for both retinopathy and nephropathy, yes condition. Now let us check another condition. Like the gender will be female, age is 43, diabetes duration is 3, smoking no, drinking no, height is 160, weight is 57, BMI will be 22.265625, SBP value is 123, DBP value is 70, HbA1c value will be 8.9, FBG value is 10.29, TG value will be 3.81, C-peptide value is 0.64, TC value will be 4.1, HDLC value is 0.84, LDLC value will be 1.85, insulin is yes, metformin is yes, liquid lowering drugs is also yes. Now click on predict retinopathy so that the input is pre-processed and the output will be displayed as no retinopathy and no nephropathy. The confidence level is 95.7% and 97.4%, which means it is a good news and annual checkups and regular monitoring is needed. We also have no retinopathy detected, what this means, and preventive measures, when to see a doctor, and no nephropathy is detected for that. What are the preventive measures are taken and drug recommendations, preventive medications are given. As we have seen the prediction modules, now let us check for classification. When you click on the classification button, the upload image for classification will be opened where you need to upload the image and classify the image. First, let us give the image. We need to give the input image from the test cases of the code folder for classification. We have two conditions like DR and no DR. Let us check by the given input and click on classify the image. The input image is pre-processed and the output is displayed as, for the given input image, it is diabetic retinopathy is detected. The probability breakdown is 100%. This is the original image. This is the grad cam visualization. Now click on try another so that the form will be opened where you can upload the other image. Now let us check by giving another image. Click on classify image so that the input image is pre-processed and the output will be displayed as no diabetic retinopathy. The probability breakdown, like no diabetes, is 100%. This is the original image which we have uploaded, and this is a grad cam visualization. Now click on data visualization. We have three different graphical representations for classification and for retinopathy and nephropathy. So first let us go with classification graphs. First we have accuracy graph. The graph compares the accuracy of different deep learning models used for diabetic retinopathy image classification. All models show very high performance with exception and the ensemble model achieving the highest accuracy, indicating strong feature extraction and generalization ability. The ensemble models slightly outperform individual models, demonstrating that combining multiple architecture improves overall prediction reliability. Next, we have precision graph. The graph illustrates the precision scores of different deep learning models for diabetic retinopathy image classification, indicating how accurately each model identifies positive cases. All models achieve very high precision with exception and the ensemble model reaching nearly perfect values, showing minimal false positive predictions. This demonstrates that ensemble learning enhances reliability by combining the strengths of individual models. Next, we have recall graph. The graph shows the recall performance of different deep learning models in detecting diabetic retinopathy cases. Exception DenseNet 121 and the ensemble model achieves near perfect recall, indicating their strong ability to correctly identify most positive cases with very few false negatives. This is especially important in medical diagnosis as higher recall reduces the risk of missing patients with the disease. Next, we have F1 score graph. This graph compares the F1 scores of different deep learning models used for diabetic retinopathy classification, reflecting a balance between precision and recall. Exception and ensemble models achieve the highest F1 scores, indicating consistently strong and reliable performance across both metrics. This shows that ensemble learning provides a more robust classification by effectively reducing both false positives and false negatives. And next, we have retinopathy graphs. First, we have correlation matrix graph. The correlation matrix visualizes the relationship among clinical features and diabetic complications, whether warmer colors indicating strong positive correlations and cooler colors indicates negative correlations. Strong correlations are observed between related psychological measures such as weight and BMI, HbA1c and fasting blood glucose and lipid profile components confirming clinical relevances. Diabetic retinopathy and nephropathy shows moderate correlations with diabetes duration and glycemic indicators highlighting their importance as key risk factors in complication prediction. Next, we have sample outcomes graph. The pie chart represents the distribution of diabetic nephropathy outcomes in the dataset. A majority of samples belongs to the no classes, indicating patient without nephropathy, while 38.07% represents patients with diabetic nephropathy. This shows a moderate classes imbalance, which justifies the use of resampling techniques during model training. Next, we have confusion matrix and ROC curve graph. The confusion matrix shows excellent performance, 1001 correct, no, and 991 corrects, yes, predictions, with only 8 total errors. This means the model has very high accuracy, with both false positives and false negatives being minimal. ROC curve has an AUC of 1.00%, indicating near perfect ability to distinguish between two classes. Next, we have accuracy graph. The graph compares the accuracy of multiple machine learning models trained on original oversampled and undersampled datasets. Models trained on oversampled data consistently achieve much higher accuracy than those trained on original or unsampled data, highlighting the importance of handling class imbalance. The ensemble of ensemble model achieves the highest accuracy overall, demonstrating the effectiveness of combining multiple optimized classifiers for robust prediction. And next we have precision graph. The graph compares precision score of different machine learning models trained on original oversampled, undersampled data sets and an ensemble. Oversampling greatly improves precision for most models, while undersampling generally reduces precision compared to oversampling and original data. The ensemble model achieves the highest precision overall, indicating that combining models yield the most reliable prediction. Next, we have recall graph. The graph compares recall scores of different machine learning models across three settings: original data, oversample data, and undersampling data, plus a final ensemble. Oversampling dramatically improves recall, with almost all models reaching near perfect recall compared to much lower recall on the original data. Undersampling gives moderate recall improvements, but not as strong as oversampling, while the ensemble of ensemble achieves the highest recall overall, showing the benefit of combining models. Next, we have F1 score graph. The graph shows F1 scores of multiple ML models under original, oversampled, and undersampled data settings, highlighting the balance between precision and recall. Oversampling yields the strongest performance, with nearly all models achieving very high F1 scores, indicating both accurate and consistent classification. Undersampling provides moderate improvement over original data, but the ensemble of ensemble achieves the best overall F1 score, demonstrating the effectiveness of combining multiple models. Next, we have ROC-AUC graph. The graph compares ROC-AUC scores of various ML models across original, oversampled, and undersampled dataset, measuring each model's ability to distinguish between classes. Oversampling leads to near perfect ROC-AUC for almost all models, showing excellent class separatability compared to moderate performance on the original data. Undersampling improves ROC-AUC but remains less effective than oversampling, while the ensemble of ensemble achieves the highest possible, indicating the most robust overall discrimination. Next, we have log loss graph. The graph compares log loss across many ML models trained on original, oversampled, and undersampled dataset, plus an ensemble. Models trained on oversampled data generally achieves the lowest log loss, indicating better probability predictions, while undersampled models often perform worse, with some showing very high log loss. The ensemble of ensemble achieves one of the best log loss values, suggesting that combining models improve overall predictive performance. Next, we have explainable AI SHAP graph. This SHAP summary plot shows feature importance and direction of impact on the model's prediction, where features at top have the strongest influence. Color indicates feature values. Points to the right increase the predicted outcome, while to the points left decrease it. For example, higher diabetes duration and blood pressure tends to raise the model output, whereas metformin use and favorable lipid markers often reduces it, showing clinically meaningful patterns. Next, we have explainable AI water plot graph. Explainable AI water plot graph. This bar chart ranks features by mean absolute SHAP values, showing their overall importance in influencing the model's prediction. Metformin, diabetes duration, and systolic blood pressure are the most influential features, contributing the largest average impact on model output. Features like smoking and lipid-lowering drugs have relatively small SHAP values, indicating minimal influence on the model compared to clinical and metabolic variables. Next, we have nephropathy graphs. In this, first we have correlation matrix graph. This correlation metric shows the strength and direction of relationship between clinical and lifestyle variables, where Values closer to plus or equal to 1 indicate stronger correlations. Notably, positive correlations include weight, BMI, height, weight, and HbA1c, FBG, while smoking or drinking shows negative correlations with gender. Most other correlations are weak, suggesting limited multicollinearity among the majority of features. Next, we have sample outcomes graph. This pie chart shows the distribution of diabetic nephropathy outcomes in the sample. About 74.05% of patients do not have nephropathy, while 25.95% are diagnosed with DN. This indicates the DN cases from a smaller but significant portions of the data set. Next, we have confusion matrix and ROC curve graph. The model correctly classifies almost all cases with only 3 misclassifications, shows very high accuracy. There are 2 false positives and 1 false negative, meaning mistakes are extremely rarer and well balanced. ROC curve. The curve reaches the top left corner with AUC of 1.00%, indicating perfect class separation and outstanding model performance. Next, we have accuracy graph. The original models achieve moderate accuracy, showing limited performance on the imbalanced data. Oversampling dramatically improves accuracy for all models, pushing most of them close to perfect performance. Undersampling generally lowers accuracy, while the final ensemble model achieves the highest overall accuracy. Next, we have precision graph. The graph compares the precision of different machine learning models across 3 settings: original data, oversampled data, and undersampled data. Models trained on oversampled data generally achieves much higher precision than those trained on original and undersampled data, showing the benefits of handling class imbalance. The ensemble of ensemble models perform best overall, reaching the highest precision among all models. Next, we have recall graph. The graph shows the recall performance of different machine learning models using original, oversampled, and undersampled data. Recall is generally low for models trained on the original data, improves dramatically with oversampling, and remains moderate with undersampling. The ensemble of ensemble model achieves the highest recall, indicating the strongest ability to correctly identify positive cases. Next, we have F1 score graph. The graph compares the F1 scores of different machine learning models across original, oversampled, and undersampled data sets. Models trained on oversampled data achieves the highest F1 scores, showing a strong balance between precision and recall, while original data model performs the worst and undersampled models fall in between. The ensemble of ensemble models achieve the best overall F1 score, indicating the most balanced and reliable performance. Next, we have ROC-AUC score graph. The graph compares ROC-AUC scores of different machine learning models trained on original, oversampled, and undersampled data. Models trained with oversample achieve near perfect ROC-AUC scores, showing a large performance improvement over the original and unsampled versions. The ensemble model performs the best overall, indicating that combining multiple models yield the strongest and most reliable classification performance. Next, we have log-loss graph. The graph compares log-loss scores across models trained on original, oversampled, and undersampled data, where lower log-loss means better probability prediction. Oversampled models achieve dramatically low log-loss values than the original and undersampled models, indicating much stronger and more confident performance. The ensemble model has the lowest log loss overall, showing it provides the most accurate and well-calibrated predictions. Next, we have explainable AI SHAP graph. This is a SHAP summary plot which shows how each variable influences the model prediction and how important each variable is overall. Features at the top have the biggest impact, and dots to the right increases the prediction, while dots to the left decrease it. Color shows whether the feature value is high or low. In short, the model's output is driven most by lipids, diabetes-related factors, and blood pressure, while factors near the bottom have much smaller effect. Next, we have explainable AI water plot graph. This bar chart shows global feature importance based on mean absolute SHAP values, where taller bar means the variable has a stronger overall influence on the model's prediction. HDLC, diabetic duration, styolic blood pressure, and HbA1c are the most influential features, indicating the model relies highly on lipid levels and diabetes related factors. Features near the bottom contribute very little to the model's prediction. Then click on sign out. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.